While we get set up here, my name's P Lanyon. I'm an ion trapper from Innsbruck in Austria, and I also would like to thank the organizers for inviting me here. It's always a great pleasure to speak at this conference in particular, and thank you to you in the audience for making it here despite the transport issues going on outside. I appreciate it. I know it's not so easy. Okay, so I want to get straight into it and explain our engineered many-body quantum system that we work with. We work with 1D strings of atomic ions in 3D radio frequency linear Paul traps, and so that's an image of maybe 15 calcium-40 ions. And inside each, we encode a spin-half particle or a qubit. Here is an energy level, simplified energy level diagram of the single outer valence electron. Once we get rid of one of the electrons, we're left with a hydrogen-like structure, and here are the energy levels that are relevant. We encode our spins in an S1/2 ground state and a D5/2 metastable state. Lives for about a second, and the things we do are much faster than that. It's connected by an optical quadrupole transition at 729 nanometers, and so if you come into our labs in Innsbruck, there's quite a few 1 hertz and sub-1 hertz line width 729 nanometer lasers. And so what we have here is a one-dimensional chain of qubits, of spin-half particles. And we can read out the qubit states individually via the standard electron shelving method. We shine in ultraviolet light on this transition and look for whether we see a bright or a dark ion, and this tells us whether our spin is up or down. And yeah, we can do that for any individual ion, as you can see in these images here, because our ions are several microns apart. We can individually control each ion and each qubit in each ion, up to about 20 at the moment. We can do full single qubit control with tightly focused lasers generated via acousto-optic deflectors that can simultaneously manipulate up to 20 ionic qubits, and we're working on improving our optical system over the next couple of months to extend this up to 50, and we can trap quite stably and work with chains of 50 spins in this system. And so here's a real-time movie of kind of quantum jumps in this. I think there might be 20 calcium-40 atoms here jumping between the metastable, the ground and the metastable state. As has been mentioned so far, the qubits don't interact very strongly. They're very far apart, as many microns. And so what that means is that this qubit in this ion over here doesn't feel any difference or any energy difference about the state in its neighboring ion, the electronic state. And so our qubits don't interact on their own, so there's no entanglement coming for free or any significant entanglement. But we can turn on these interactions between our spins using lasers that off-resonantly drive all of the, in this case, transverse normal modes of motion simultaneously in the system, far off-resonant driving. And via that off-resonant driving, you can go through some maths, and you come up with effective spin-spin interactions between spins that are a distance d apart that decays with a power law. So it depends on the distance to some power. And we can tune that power law all the way from infinite range interactions, so alpha is 0, to effectively short-range interactions, 1 over r cubed. And go from physics where you have nearest neighbor type interactions to long-range interactions. And I don't have time to explain this, but essentially you can tune it via how far off-resonant you drive these motional modes. Okay, so here are some of our experimental results in recent years. Over here, we have a 15-spin system, and we prepare it in the ground state of some Hamiltonian, which happens to be a product state, all spins down, and we put an excitation right in the middle. We flip one spin, and what you're seeing here is experimental data showing this spin excitation, this magnon quasi-particle, coherently dispersing inside the system and bouncing off the boundaries and creating these beautiful interference patterns. It's a little bit like a one-dimensional quantum walk. And we were able to show that these wavefronts, which appear in this short-range interaction case, are propagating entanglement waves across the system. They're distributing entangled bell pairs right to the boundaries of the system. And then more recently, we've been looking at putting in spin excitations at every second site. And each of these sites now in the outer vigulum dynamics that we turn on acts like a little source of quantum entanglement, spitting out correlations left and right. And so at early times in the dynamics, we end up with kind of locally correlated many-body entangled states. And so what this allows for is the opportunity for us to broadly engineer and probe in a single particle way many-body quantum states and dynamics. But we need already new methods to both verify what's going on in the lab and to probe and access the quantum phenomena that we're interested in. Your quantum state tomography and these methods, they break down. They're too inefficient for these larger systems. And in particular, what we want is methods to probe entanglement and the structure of entanglement in these systems. We know that according to the standard model of quantum simulation and quantum computation, that such devices must generate large amounts of entanglement in their dynamics, otherwise you can follow them efficiently on a classical computer. And so we would like methods to probe and see that such systems can generate entanglement and large-scale entanglement as far as possible. And this doesn't just apply to trapped ions, but also many other engineered quantum systems that people are working on, and we've heard about them, many of them in this conference. Okay, so we've made 3 recent contributions to this. I'm not going to talk about the first 2. I'm going to go straight to the third, probing entanglement entropy via randomized measurements. Our paper's just come recently out on the archive, and it was a nice collaboration between our experimental teams and the Entanglement Entropy department of Peter Zoller's group. And in it, we present and demonstrate a new protocol to measure the overall coherence of a quantum system and the entanglement between its parts. So I'll start with a definition of Rennie entropy. A few people have mentioned it. So the Rennie entropy is the density matrix of the system you're interested in, rho, to some power n. You take the trace, you take the log to your favorite base, and this is the Rennie entropy. And in the case of pure states, the higher order Rennie entropies are 0, and in the case of mixed states, they're greater than 0. So it quantifies somehow how much mixture is in the system. And for the case where n is 2, you might recognize this as just the purity of the system, trace rho squared. There's a deep connection between entropy and entanglement. If I have a many-body quantum system in a pure state, an overall pure state, and I just look at the state of a part of it, and I see that it is now mixed, then I know that that's because there are quantum correlations between that part and the rest. But in the lab, we don't generate perfectly pure states. There's always a bit of mixture, and so there's a more general proof that you can find in this paper that says if the entropy of part of the system is greater than the entropy of the whole, then there's bipartite entanglement across that partition. And so we're interested in measuring Rennie entropy differences to reveal the bipartite structure in interacting quantum systems. Okay, so how do you measure Rennie entropy? It's a nonlinear function of the density matrix, which makes it very hard to measure. We only measure linear observables. One approach is to do full quantum state tomography and just measure everything. Reconstruct your best estimate of the quantum state and take the trace to various powers. For the case of weakly entangled states and other types of simple states, there are scalable methods to do this in the lab. But for the more general case, and I would say the more interesting case of strongly entangled states, this method does not scale well, and already for about 8 qubits, which is the experimental record, I think, achieved in Innsbruck, this was already quite a hero experiment, and going beyond 8 qubits, this seems infeasible. There's a very, very clever method called the copy method, where you make 2 copies of your interacting quantum system, 2 identical copies, and then you do a clever interference measurement between them, and then from the local measurements results, you can pull out trace rho squared. And this is great, provided that you can make multiple simultaneous copies of your quantum system and do the interference as well, which is non-trivial. However, this was done in a series of beautiful experiments in the group of Markus Greiner, using a controlled few atom system and a quantum gas microscope. We propose, and we've demonstrated, in some ways a simpler method, a different method for sure, to to measure entropies that requires only a single copy of the quantum system. And in this case, one can get access to the Rennie entropies from statistical correlations between the outcomes of measurements performed in randomized bases. And we present a new protocol building on previous theoretical ideas that can be implemented in any platform, not just trapped ions. And we used it to access some states of a size of complexity that were beyond our reach in our system. OK, so here is the original proposal by Van Enck and Benneker, where you want to get the Rennie entropy of some system prepared in some state rho A. You do a randomly chosen multi-qubit unitary operation and measure the logical state. And then you repeat this experiment to get measurement statistics, and you can get an estimate for the probability of getting a particular logical state outcome. And these guys showed that the logical probabilities squared averaged over randomly drawn multi-qubit unitaries gives you trace rho squared. So somehow the information is in the noise of the measurements here. This is a very impressive piece of work and led to all of this. In reality, at the moment, it's extremely challenging to implement multi-qubit unitary operations by decomposing them into complex logic gate sequences. The step that really made it work for us now is showing that it's possible to do this using only single spin rotations. And in this case, so I hope this is clear, you don't have to do a multi-qubit unitary, you just do single spin rotations, which effectively just change the measurement basis that you make here. And in this case, we prove in the paper that the information about the entropies are contained in cross-correlations between the probabilities of getting different logical outcomes averaged over randomly drawn unitaries. And then in the paper, we provide an explicit relationship between the measurement, the outcomes of the measurements, these probabilities or probability estimates, and a random variable, and you take the average and you get the entropy. So there's no complex post-processing required. So we thought that we would implement this and do it in the most complicated way possible. So we start off with a product state of our ionic spins, with a product state that's a superposition of many eigenstates of some interacting Hamiltonian that we turn on with laser fields, and then turn on those interactions. And so this is like a global quench. And in the out of equilibrium dynamics, we make complex many-body states, and the entanglement just continues to grow until it saturates in the system. And that's what we do until here. So we can turn off the interactions after some time t, freeze the quantum state, and then use this protocol of random measurement bases to pull out the entropies. And actually, by this type of measurement, you can pull out the entropies of all possible bipartitions of the system from one set of data. OK, so here are the results. So this is for a 10-spin system, a little bit larger than what we could access before with quantum state tomography. Here's a graph. On the vertical axis is a trace rho squared, so the purity. So 1 is pure and not 1 is mixed. And on the horizontal axis here, we have the partition that I'm talking about. So 1 would be this spin. 2, the point 2 here would be these 2 spins. Point 3 would be these 3 spins, all the way up to point 10, which is the purity of the whole system. And this is for the initial state, this initial product state. And we hope, well, we try to make this product state. So we don't expect there to be an entanglement there. And we expect to have something, well, ideally a pure state. And we're very happy with these results, because this corresponds to a total purity of 76%, which is extremely high for a 10-qubit state. And it corresponds to something like a 1% error on each spin of flipping and making the right product state. And also, because the purities are higher of all of the subsystems, it's consistent with a product state. We can't see any entanglement here, as we would expect. And then we turn the interactions on. And what we see, first of all, is the purity of the overall system remains high. So we have unitary evolution to within the error bars, whereas the purity of the subsystems goes down, signifying the generation of entanglement between those partitions. And then as time goes on, further and further, the amount of entanglement and the depth of entanglement continues to grow. And ultimately, we start to reach, in the 1 and 2 spin reductions, maximally mixed states set by the Hilbert space dimension. And of course, you can take the second logarithm of this and pull out the Rennie entropy. I would say it's very clear from this work that not only do we have unitary dynamics for the extent that we look at it, but there is lots of entanglement being generated between the bipartitions that I'm presenting. And in the lab, this took, if we tried to do it by state tomography, this would just take weeks and weeks and weeks and weeks, and the post-processing may actually still be running. But by this technique, it took around 10 minutes with our repetition rate to take each of these lines. Okay, so there are many more possible bipartitions of this 10-qubit system, something like 500. And so this actually is from the same set of data after 5 milliseconds of out of equilibrium dynamics. This is the entropy of all possible bipartitions of this 10-qubit system. So here is the one way that you can have 10, yeah? And then all the different ways of having other groups of particles. And you can see clearly, statistically, significantly, there is entanglement in every possible bipartition of this system. Okay. And so then we extended the size of the system to 20 spins, and now we look at the middle 10. And we turn on this quench dynamics again. And now in this case, not only can there be entanglement generated between these 10 in the middle here, but also entanglement now with the other spins. And so now the entropy is free to grow pretty much as fast as it possibly can, and we can generate maximally mixed states of these, close to maximally mixed states. This is the entropy here, maximally mixed states of this 10-qubit system. We weren't able to do entropy measurements of the whole 20-qubit system due to some technical limitations that limited our repetition rate, but it's clear to us in the next couple of months how to improve our system so that we can make 20-spin measurements of Rennie entropies. I'll skip through this slide. So in the interest of time, I just want to say that we were able to see that if we can add controllable random disorder to the system, that the rate of entanglement entropy growth was suppressed. But I'll skip past this. Okay, so to come on to summary. So I've presented randomized measurements as a tool to study engineered quantum many-body systems in the lab. With it, you can access the overall coherence of a quantum system. You can see how long it realizes unitary evolution or not. And you get the bipartite entanglement structure between its parts. It requires only a single copy of the quantum system at a time, which made a big difference to us because it would be very hard for us to make multiple copies. It works for all states, not just weakly entangled states. It works just fine for strongly entangled states, and these are the states that we're particularly interested in generating at the end of the day. And this works up to a certain system size, and I'll talk about that in a second. And it allowed us, in the lab, to probe a system of a size and complexity that was beyond reach beforehand. And as an outlook, the effort scales more favorably than state tomography. So to be clear, this is not a method to practically characterize large entanglement in a full-scale quantum system. The effort scales exponentially. But it scales much better than tomography, and it seems that in our system it would be fairly straightforward to do this with 20 spins, and in systems that have faster repetition rates, like superconducting circuits, one could imagine going to 30 or even 40 spins and being able to verify quantum dynamics on that scale. And I guess, so I envisage this as the tool to verify and probe partitions of larger many-body quantum systems. So you can check, for example, that the first 30 spins, you can see for how long the unitary dynamics is maintained, look at the entanglement growth between its parts, and repeat that for different partitions of your system to build up confidence that the parts of it work before opening up the floodgates, if you like, between these partitions and letting the system evolve into regions that you can't follow off a complexity cliff. Okay, and I just want to finish with some adverts for some other work. The first one up here was a great collaboration with the group of Markus Huber in Vienna and Martin Plenio in Ulm. We built custom entanglement witnesses and were able to see the generation of multipartite entanglement in the out-of-equilibrium dynamics of a 20-spin system. Everything I've told you about before was bipartite entanglement, but there are many more flavors of entanglement that you can do different things with, and we could see up to fifth-order five-body genuinely multipartite entanglement in the out-of-equilibrium dynamics. And last, so on a kind of different topic, both in Innsbruck and our previous work and recent work in Innsbruck, combined with recent work from other groups, it seems fairly clear now that it is possible to, or it will soon be possible, to take near deterministically a couple of photon that's emitted by one of these spins, these calcium-40 spins, that is entangled via polarization with one of these spins and connected to it in a quantum correlated way, and to near deterministically extract that photon using cavity QED techniques, and to take that photon and convert its frequency to the telecom band, and at that wavelength, and at the same time preserve the entanglement between light and matter. And at that wavelength, it seems feasible to distribute quantum correlations between these many-body processes over distances of 100 kilometer plus. And of course, we can co-trap these spin systems with aluminium, for example, and we can, I think, start to reasonably think about entangling distributed atomic clocks in the coming years. And with that, I will finish.